Okay, so in this video, we're going to go over how electromagnetic fields transform in changes of relativistic reference frame. Now, one might guess or really hope that E and B fields transform like some sort of four vector, but we talked about this in class. Unfortunately, it's not the case because, as we can recall, when we were trying to simplify Maxwell's equations, if you want to describe a point in space and time, uh, and describe the EM fields, you need six components. You need the three E fields, EX, EY, and EZ, and you need the three B fields. And of course, that's six components, not four components. As we will see, the only way to do this is to actually transform E and B fields as tensors. That's the bad news. The good news is that the formula for transforming E and B fields, once we derive it, is actually simple enough that you don't really need to understand tensors in order to do the transformation. And that's the part that I want you to walk away with in this video, is just how to transform E and B fields without not necessarily understanding the formalism of the tensors. Um, that's the good news, but then the other bad news is that getting to that transformation is a multi-step process that we are going to go through in this video. Before we move on, we need to make an explicit statement of an assumption that we've already been making, which is that charge is an invariant. That is to say, not charge density. We're going to see charge density can vary from frame to frame, but electric charge, the total quantity of charge, is an invariant that is the same in all reference frames. So if I have a charge of 2 coulombs, no matter what reference frame I'm in, there will be 2 coulombs. They might be distributed differently, but the total amount of charge is going to be conserved. One other point that we need to make is that E and B fields transform the same way regardless of how they were created. What I mean by that is I could create an E field using a charge or a charge distribution, but I can also create an E field from a time varying B field. Similarly, I can create a B field from a current or from a time varying E field. Whatever the underlying cause, if I'm in a frame of reference that has a particular E or B field, it will transform if I go to a different reference frame the same way that it would if the cause was a different cause, but it had the same effect as in the one reference frame before I boost into a different reference frame. Okay, now before we dive into this derivation, I want to give you a little bit of a forewarning or explanation of what's going on. The first thing is that really this derivation, which is taken largely from the textbook, is a vibe derivation. What I mean by that is we're not going to actually derive fundamentally a sort of fully generalized expression for how to transform E and B fields. What we're going to do instead is we're going to use a simple example, and through that example, we're going to kind of infer what the transformation is. Okay, it's worthwhile to still do that basic example because we will learn a lot in the process. But you should realize that this isn't a formal proof or a real first principles derivation. We're taking a special case that happens to be simple, and from that special case, we're going to learn out the essential elements of how E and B fields transform. Okay. So we're going to start with a simple system that consists of two infinite plates. Okay, and this is our coordinate system. The distance, the distance d separating these two plates is in the y direction, and they're infinite in the x and z direction, which run along or parallel to the planes. And the two planes have a plus and minus charge density of sigma naught, and you'll recall that the E field for such a configuration is just given by sigma naught divided by epsilon naught, and it'll be pointing in the y direction. But we're talking relativity. So we need to be very specific that we're talking about a particular reference frame. We're talking about the reference frame that we're going to, for the rest of this derivation, call S naught. S naught is the rest frame with respect to these plates. So the plates are not moving in this reference frame, and we are not moving relative to these plates, which of course are relativistically equivalent. We are stationary with respect to these plates. And so this is the stationary E field. And furthermore, since we're not moving, since there's no motion, there's no current. And since there's no current, there is no B field. There's only an E field. Okay. But now we're going to boost. We're going to boost from the rest frame with respect to the plates into a new frame S by moving to the right, that is moving in the X direction with a some velocity. So now we are moving relative to these plates. And even neglecting the nuances of relativity, even thinking kind of almost in a more Galilean or just obvious way, you can already anticipate that there are going to be some interesting differences. Because we are moving, that means that from our frame of reference, we're stationary and the plates are moving. And if the plates are moving, the plates carry charge, that means that there's a current flowing. And if there's a current flowing, we would expect there to be a B field, okay? Now, we're not there yet, but just keep that in mind as we go on, okay? Let's first focus in on the E field. If we boost into this frame S, our new E field is going to be sigma over epsilon y hat. To be clear, I've used sigma rather than sigma naught. Sigma naught represents the charge density at rest. Sigma represents the charge density in frame S. Now, why is the charge density in frame S different? Well, if we're moving, then we are going to experience, there's going to be length contraction in the direction that we're moving, which means that a given length of these plates is going to be smaller, which means that there's more charge per unit length in these plates. And so this sigma here is actually going to be higher than in the stationary case, which means we're going to actually be experiencing a higher E field. And the relationship is the new sigma is equal to the old sigma times gamma. So this sigma is the new charge density due to length contraction in specifically the direction of motion. There's more charge per unit length in the direction of motion, as we just said. And so the charge is concentrated in a more compressed interval. This increases the E field, and this is the first interesting observation that we're going to make. The length contraction, of course, is in the direction parallel to our motion, but the effect is going to be to increase the E field, but the E field is pointing perpendicular to our motion. So the act of moving or boosting into a moving frame makes the E field larger, but larger in a direction that's perpendicular to our direction of motion. In other words, E perpendicular is equal to gamma times E, the new E perpendicular. I should actually put a no, this is the right notation. This just needs a naught. E perpendicular in S is equal to the E field in at rest times gamma, the gamma naught of that. So to understand, and by the way, when I say gamma naught, of course you know the formula is 1 over the square root of 1 minus v squared over c squared, where here v is the speed of S relative to S naught. Okay, it's the speed at which this new frame of reference is moving relative to the stationary frame. Now, to understand what happens or how the parallel component of the E field transforms, it's instructive to think about what happens if we are traveling, if we are traveling in the direction parallel to the E field, which is perpendicular to the plates. Well, what would happen? If we were moving in the direction parallel to these plates, we would experience length contraction, which would make d smaller. But what do you notice about the E field? The E field's magnitude does not depend on the distance. And so whether or not the distance is smaller doesn't affect the E field. In other words, the parallel component of the E field is the same. So when we boost in the direction, if we were to travel in a direction parallel to the E field, then the E field wouldn't change when we boosted. So to recap, if we are traveling in a direction perpendicular to the E field, then the E field will change in the direction perpendicular to our motion by a factor of gamma. But if we boost in a direction parallel to the E field will not change. Okay, so that's the E field, but it's not just that we see a change in our E field. We're going back to now motion in the x direction, so we're in this frame S that's moving in the S direction. And if we're moving in the direction positive x, then from our frame of reference, we're standing still, and those two plates are moving backwards in the x direction, and therefore we see a current density going backwards of negative plus sigma v naught x, where sigma, of course, is the new sigma. It's the charge density in our current frame of reference, times v naught, which is our velocity relative to the stationary frame, which is also, by the way, because of symmetry, the stationary frame of reference is velocity relative to us. And that current density, of course, is going to be in the x direction, opposite the direction that we are traveling. And with this current density, the B field will be pointing in the z direction, and it will end up being negative mu naught sigma v naught. And this is just magnetostatics. Okay. Now, this is a multi-step process, and we've boosted from the stationary frame into a frame where we're moving. And in the frame where we're moving, we have some combination of E and B fields. To finish the process, to fully understand how E and B fields transform, it's instructive to start in a reference frame where you have a mixture of E and B fields and then boost to another frame. So we're going to boost to a third frame that we're going to call S bar from S. So we're going to start in a frame of reference where we already have a magnetic field and an electric field. And then we're going to ask the question, if we boost to this new frame, S bar, how do the different fields transform? And S bar is going to be traveling relative to S at a velocity v. Just to show you this picture, S is going at a velocity v naught with respect to S naught. So S naught is the frame in which the two plates are stationary. S is the boosted frame that we just calculated, where now there's a slightly higher E field in the Y direction and also a B field in the Z direction due to the current. And so that's where we are now. And we're going to ask the question, if we boost to frame S bar that's going at velocity V relative to frame S, what E field and B field do we see? So the E field is going to, of course, be sigma bar E naught, and the B field is going to be negative mu naught sigma bar V naught, where V naught is the, I'm sorry, not V naught, V bar. V bar is the speed of S bar relative to S naught, okay? And by velocity addition, we can actually write V bar in terms of its relation to the stationary frame. It's equal to the velocity of S plus, or sorry, the velocity of S bar relative to S plus the velocity of S relative to the stationary frame S naught divided by 1 plus VV naught over C squared. So this is the velocity V bar of S bar relative to the stationary frame, and the corresponding gamma is going to be 1 minus V bar squared over C squared. And in this frame, the new charge density is going to be equal to gamma bar that we just defined here times the stationary or the rest frame charge density. And so if we want to write uh, EY bar, we can write it as basically being equal to the ratio of gamma bar to gamma naught times sigma epsilon naught over epsilon naught. So this is the charge density in frame S divided by epsilon naught. If we divide by gamma naught, that takes us back to the stationary frame. And then if we multiply by gamma bar, that takes us to the S bar frame. So this takes us into the S bar frame. And we can do the same thing or a similar thing to get BZ in the S bar frame. Now, the ratio of gamma naughts to gamma turns out to be the ratio of square root of 1 minus v naught squared over c squared to 1 minus v bar squared over c squared. And this is a funny line in the Griffiths. He says, with a little bit of algebra, you can derive this. Now, I'll tell you, I went off and tried to do it and eventually succeeded. It took me so long that I'm not even going to include it in my notes, but it is not exactly a little algebra. You have to kind of substitute in this formula for v bar here. You have to do a bunch of multiplication, refactorization. But just take my word for it that it comes out to this formula, where gamma is 1 over 1 minus v squared over c squared. Okay. Now, what did we just do here? Well, we were talking about v bar, the velocity of the frame s bar relative to the stationary frame. But what this formula does is this tells us this ratio here for specifically in terms of the velocity of s bar relative to s, which is v, and then s relative to s naught. So if you know this velocity and this velocity, you just plug them into this formula. And of course, this gamma depends only on this velocity here, the velocity of s bar relative to s. Okay, so we now have a formula that we can substitute into these two equations for the E and the B field. And now let's do it. EY bar is equal to gamma over gamma naught sigma epsilon naught over epsilon naught. And that's equal to gamma times 1 plus VV naught over C squared times sigma over epsilon. And here's where things get interesting. 1 times sigma over epsilon is EY. So I could rewrite this as EY. And VV naught times over C squared times sigma over epsilon can be rewritten as negative V over C squared epsilon naught mu naught times negative mu sigma V naught, because these mu's cancel, and the sigma that's here comes from this, and this V naught is here, and this V is here, and then of course we have the epsilon naught and the C squared. So this is just a weird like algebraic expansion and manipulation of this term. But of course, epsilon naught mu naught times c squared is equal to 1. And this is the expression for BZ, the magnetic field in frame S. So we have that the electric field in frame S bar is equal to gamma times the y component of the electric field in S plus V times the magnetic field in the z direction. Okay, so we can rewrite this, and voila, we have our expression that shows how EY bar is transformed. Now, I want you to think about what this says. This says that the new E field in the y direction is equal to gamma times the old E field. That kind of makes sense. But minus V times gamma times BZ. So this transformation it intermixes the E and the B fields. Again, you can kind of think of this as a rotation, except it's kind of super complicated because it's a tensor rotation. But it's a rotation in the sense that you start out with one composition of E fields and B fields, And then in the boosted frame, you have a new E field that depends on what the E and the B field were in the previous frame. And you'll also, as we'll see, have a new B field that is a mixture of the B and E fields as well. So here's the expression for BZ. We fill in the gamma times this stuff times the current. We do some algebraic manipulation, and I'm kind of skipping steps, but what we get to is that the new B field in S bar is equal to gamma times the B field in S minus V over C squared, where V is the velocity of S bar with respect to S, times EY. So there you have it. Now that gives us the transformation of the Y component of the E field and the Z component of the B field for a boost in X. Let me say it again. If we boost in the X direction, this tells us how to transform the Y direction of the E field as being some combination of the old Y component of the E field minus V times the previous Z component of the B field. And we have a similar one for B. Now, if we want to know what happens in the other directions, um, and I think I wrote this wrong. I think this is for EZ and BY. Let me fix that. Oh man, hold on. So this is for EZ and BY. We can keep the same motion that we were doing. We were moving in X, but let's now orient the plates this way instead of this way. And when we do that, if we do the math, you'll have to take my word for it, but it works out that we get that EZ bar equals gamma EZ plus VBY, and BY bar equals gamma BY plus B over C squared EZ, which has its similarities to these terms here. And so now, just to recap, we have, if we boost in the X direction, we have a way of writing EY bar in terms of EY and BZ. And we can write BZ bar in terms of BZ and EY, but we can also write EZ in terms of EZ and BY in terms of BY and EZ. So we've got the transformations in the of the E and B fields in the two directions that are perpendicular to the direction of motion, Z and Y. And we already earlier derived, but we can look at it again, that if we're moving in the X direction parallel to the E field, the field remains unchanged. Now, not only is this example not a fully rigorous and universal proof, but it's not even complete because we can't even use this geometry to describe the transformation to the B field with a boost in a direction parallel to the B field. For that problem, we're going to imagine a relativistic solenoid. So we have a solenoid that's going at a velocity v, and that means that the boost direction is in the direction of the B field. Now, in this case, what happens? Well, if we boost to a frame where the solenoid is moving relative to us, length contraction means that the density of turns of the solenoid is going to get higher, which would increase the B field. But remember that the B field is produced by a current, which is charge per unit time, and I, the current, experiences time dilation of 1 over gamma. So the factor of gamma times the turn density multiplied by 1 over gamma times the current, the gamma factors cancel out, and we end up getting that the B field in the parallel direction also remains unchanged. With that now, we can actually write out the full set of equations for the transformations of E and B fields for a boost in X. If we boost in the X direction, If there's an x component of the E field, it remains unchanged. If there's an x component of the B field, it remains unchanged. But if we boost in the x direction, the y component of the E field changes by a factor of gamma times the previous y component of the E field, that is the E field in frame S, minus v times the z component of the B field in frame S. And similarly, by is gamma by plus v over c squared ez. And then ez is going to be gamma ez minus vby, and bz bar is going to be gamma bz plus v over c squared ey. These are the equations that I want you to remember and be able to use. They're fairly straightforward because if I describe to you an E and B field in a particular frame, and then I say that I'm boosting to a frame going at some speed relative to those fields, you calculate the gamma for that particular um, uh, speed, and then you just figure out the parallel and perpendicular components and you go and apply these relationships. Now, if I want to say this in its most general term, what it tells me is that in the direction parallel to the E and B field, the fields don't change, but in the perpendicular directions, the formula is equal to the perpendicular E field in the prior or in the original frame of reference plus v cross b perpendicular. That's what gives us the pluses and the minuses. And similarly, b perpendicular is equal, in the new frame, s bar is equal to gamma times the b field in the old frame, s, minus v over c squared crossed with e perpendicular. Finally, I just want to bring your attention to two special cases. If in frame S the B field is equal to 0, then in frame S bar, B bar is just going to be negative 1 over C squared times V cross E. And if the E field is 0 in S, then when we boost to S bar, the E field will just be equal to V cross B, which, by the way, you can see in that the kind of the Lorentz force equation, the QV cross B. Now, this is really nice from a problem-solving standpoint because it gets us an easy way to derive the B and the E fields. It's similar in problems that we were doing with kinematics, where we would start out in the rest frame of the particle, in which case its momentum is 0, but its energy is just equal to its rest mass times c squared. And once we start in that frame, then if we want to extrapolate what happens in another frame, then we just apply the Lorentz transform. But we can start in that simple frame where momentum is 0 and energy is equal to the rest mass, and then we can boost to a frame where it's more complicated. Similarly, if you can find a frame where either the B or the E field is 0, then you can use these relationships generally and these relationships in particular to figure out what the new B or E field would be in a boosted frame of reference. And that is basically the most important essence of how E and B fields transform. I want to just say philosophically, this is really fascinating. And I want to bring your minds back to the example I talked about in class, where you had essentially a current in a neutral wire. But then if you were to move and boost into a moving frame, the stationary positive charges of the wire would compress, and assuming that your boost speed is at the same speed as the current, then the electrons that are moving along with you, those are not stationary, or not moving away from you. They're stationary because they're in the same frame of reference as you, and so they do not experience space length contraction. So if the positive charges have a length contraction and the negative charges don't, you get a net negative charge density. So remember in that wire problem, you went from a neutral wire with only a B field, and you boosted into a frame where you might have a different B field, but you also have an E field due to the fact that you now have a net charge density. And so, that example, like this example, what it tells you is that different observers in different frames of reference will see different combinations of E and B fields. But the remarkable part is the observers will agree for the most part on what the kinematic effects of those are. There are a few subtleties with how forces are done in relativity, but like in broad terms, it's really interesting that in my wire analogy, the in one frame you experience a magnetic field, and in the other frame you experience an electric field that is pointing in the same direction as the magnetic field. And so again, the observers actually ultimately agree on the behavior of the charge that it's experiencing these forces, but they disagree on the particular composition of how much of the force is from the E field and how much is from the B field. They each see different mixtures of E and B, but there are aspects of the dynamics that the E and B field cause that are the same in all frames of reference. And again, these are the operative formulas you need to have and be able to use.